All right,
now.
perfect. Then, yeah, welcome everybody to second meeting of the online culture seminar, and it's my pleasure to introduce Khalil Ghorbal, uh, who will speak about characterizing positively invariant sets, about inductive and topological methods.
Well, thank you very much for the invitation. Thank you for having me. I'm saying actually Professor Sid, so it's not gonna be about DAEs. Let me just set up the context before diving into the positively invariant sets. Nonetheless, I would love to see those techniques work on DAEs as well. What are positively invariant sets? So maybe first, as I said, this is not about DAEs per se, but we do use all sorts of symbolic computations that might work as well for DAEs. But the settings for this talk are going to be ordinary differential equations. So for now, I just stick to general ordinary differential equations in the sense that I won't say later on, I will specify that the right-hand side is going to be polynomial, but for now, I'm allowing myself to take any fi. So fi are simply continuous functions in x1 all the way to xn. I'm using x prime it just stands for dxi over dt, so this is time derivation. I want to be using any other sorts of derivations, so this is the prime will be essentially the derivation with respect to time. So those are really autonomous systems. What else I want to say? And I will all the time, whenever I need this entire vector field, I'm going to just simply write it down in a vectorial sort of notation. So x prime equal f of x, but this means that really x is a vector and f is a vector. So we all know the initial value problem. We have, so assuming a solution exists, so at least locally and is unique. So this is gonna be, so for my ODEs, the right-hand side is continuous, and I'm going to assume that a solution exists and is unique. Local Lipschitz continuity is one sufficient condition to guarantee this property, but I'm not delving into under which conditions for FI this holds. I'm just going to set it up as an assumption so that the solution of my differential equations define a flow. Because all I need here for what comes next is really this concept or this notion of a flow. I'm going to note it by phi. This is kind of a custom notation. So phi dot x, meaning that I start somewhere in the space at x, and the dot stands for the time. So whenever I set up t there, it's going to be really the action of the group that takes x to phi t of x. Okay. So these functions are defined over some open intervals denoted by I of x, and they contain 0 naturally, and there is a maximum interval of existence for each x. So again, I won't discuss those problems like finite explosion problems, etc., etc. I'm staying locally where everything is defined, and the solution, the flow exists and is unique. Just to make notations easier, I'm going to use t positive, but what I really mean, of course, is I of x. So what I really mean by t positive here, it doesn't necessarily mean that the solution or the flow is defined for all positive time, but it really means that I'm looking for positive times intersect I of x. Okay, so as long as the solution is defined, and as long as I can, and I'm allowed to talk about phi of t of x, I'm doing it by just denoting t positive or t greater than or equal 0. That's just a matter of notation. So right away, what's the definition of positive invariant sets? You might intuitively know what it is, but here is just stated formally. So if I start within a set, right? So if I draw a picture, if I have a potato, which is my set S, and if I start somewhere in the set S and I follow my flow, right? I will always remain within the set S. Okay, I will never leave the set S. And I will never leave the set S for t greater than or equal 0. This is why we talk about positively invariant sets, right? So we could also likewise talk about negatively invariant sets if we go if we take t less than or equal 0. or we just simply say invariant if it's both negatively and positively invariant sets. For several practical reasons, we are almost often interested in positively invariant sets. So we start somewhere and we want really to see how the solution behaves when T moves forward. But the other concepts are interesting as well. And actually, we can play with negatively invariant sets afterwards. Okay. This is one example. So it's just a picture. You can see the vector field, which is a two-dimensional vector field. It's nonlinear. Well, in this case, I think it's polynomial. We have a shape, which is droplet-like. And one question we would like to answer, for instance, using a computer, is whether this shape is really positively invariant set for the set S. And what I want to say here is what I have in mind is formally verifying that the set S is positively invariant, in the sense that I don't really want to just draw some or simulate the system for some points. Oops. For some points in here. So I don't really want to do some finite number of simulations and then say, well, yeah, it seems to be okay. I really want to formally prove things. This is actually one motivation we had in mind when we started working into those problems. And we will go back to this example actually later on once we see those two characterizations I'm going to talk about. So this is not what I'm going to present here is not, this is not the only characterization we know about positively invariant sets. The subject is quite old. And the first theorem we, up to our knowledge, at least I can mention here is one characterization for positively invariant sets when the set S is a closed set. So we know this is known as the Nagumos Theorem. It dates back to 42. And intuitively, it says that if at each point on the boundary of S, the vector field is pointing inside the set S, I'm going to show a picture later on for some specific sets S. But the idea is, so if I have a set S, this is again my potato, I don't really need to look anywhere in the set S, but if I just stick to the boundaries, and I can talk about boundaries because here I'm considering the set S as a closed set. And if the flow is pointing towards, so it points in the interior or is tangent to the set S, right? Then the set S is an invariant set. Well, this is like hand waving, explaining or giving the intuition behind Nagumos theorem, and it makes sense, right? If on the boundary you're pushing toward or pushing on the tangent, so you're staying on the surface, it's kind of fine to characterize positive invariant sets for that. Should I pay attention to the chat if there is any question? Yeah, okay. That's for the slides are available on the website. Yeah.
Yeah. I will let you know if there will be questions in the chat.
Sure. Okay. Thanks. So here again, this intuition behind Nagumos theorem for a specific kind of sets S. In practice, we don't usually manipulate like any set S, but some sets are more interesting than others, just because they come from the applications where those things are important. So one such set is the sublevel set, which is given here. So for instance, if you take a continuously differentiable function, g, and you consider the set S here as such that g of x is less than or equal 0, then applying the Nagumos theorem, so first, this is a closed set, so I can apply the Nagumos theorem, and Nagumos theorem is going to say or to tell me that if for all x, wherever I am on the boundary, the vector field is pointing inside, so or is tangent. So this is here formalized by the gradient of j, a scalar f of x, which is nothing actually but the Lie derivative of g, less than or equal 0, then it's fine. And again, the picture is as I showed earlier. So this is the gradient. So this is g. This is the sublevel set. This is I am on the boundary. X is on the boundary. F of x, you can see here f of x is pointing inside, right? And this idea of pointing inside is captured as a sign condition with a scalar product. Okay. just to fix things. This is for smooth sub-level sets, applying Nagumos theorem for smooth sub-level sets. But again, in practice, we actually tend to manipulate sets that are in a larger class, in a sense, in the following sense. We don't necessarily have closed sets, nor open sets, by the way. And we do tend to have Boolean combinations of those things. So something of G1 positive and or G2 less than or equal 0, etc., right? So the sets I have in mind, and we do find in practice, are something of that's close to this. So my set S is all the x in, suppose, R2, okay? Sorry, x in R2, such that g of x less than or equal 0 and or so g1, g2 of x equals to 0 and g3 of x different from 0 or positive, etc., etc. You got the idea. So so this is why actually Nagumos theorem is just not enough if we want to use or to characterize or to compute or to check whether a given set S is a positive invariant set. So the first characterization I'm going to show is based, actually it's known since 2011. It's rather recent, I might say. But what I wanted to put forward here at this first section of the talk is the fact that we can actually simplify the proof by using real induction. So real induction might seem is actually not that well known as the induction over natural numbers, but the idea is the same. And I'm going to quickly go through real induction before using it to characterize positive invariant sets. So how many of you actually know about real induction or have used real induction in practice? Yeah, you see, I mean, likewise, it wasn't likewise for me. So I'm not that different. Nonetheless, it's a nice, it's a quite nice, I would call it proof technique, and this is how we use it here. So this is the induction over the reals. It's pretty tedious to read. There are many quantifiers all over the places. So what I'm going to do is I'm going to go through these three different conditions on a picture. So this is my T. This is 0. And I have here three conditions that if they are satisfied, I can right away say that PT, the predicate P of T, holds true for all T greater than or equal 0. Okay, we're going to go through them one by one. The first one says that P0 holds true. So here at 0, P0 is true. Right? So you start somewhere, it's 0 and it's true. So this one is easy and it's checked. Before going to the second one, I'm going to the third one. So the third one is telling you that for all T greater than or equal 0, so if you are somewhere here, like some point T greater than or equal 0, if PT is true there, so if PT here is true, what you're going to do is, what this condition is telling you is that there exists actually some epsilon positive such that within this open set, PT remains true, right? So any point you take on the line, you do have some open set right after it for which PT holds true. And at this point, you might say, well, this is probably sufficient, right? You start at P0, you have some open for which P of T is true. Well, you take maybe some point in here, you again have an open set for which PT of true. And again, you take a point and you move on and on and on. And then probably you might cover the entire line. Well, this is not really true. Why? Because you might have a wall. And indeed, you're moving forwards, but your interval here is getting smaller and smaller and smaller because this is only telling you there exists an epsilon positive, right? And you might go smaller and smaller and you will never pass this wall. So this is why condition 3 alone is not sufficient. You see? And this is when condition 2 comes into play, and condition 2 removes such walls. Okay, it says that if not PT is true, then there exists a positive epsilon for which there is an open interval behind for which not PT is true. So basically it's saying that if you take P0 and you move forwards, no such walls exist, right? So this is basically the real induction. This is all you have to keep in mind for now. And this is all it says, in fact, right? So there is, and if you want to compare it to the natural numbers, you start at 0. If the hypothesis holds at some point and you prove it for the next one, then you can move forward like this one, okay? But here, for practical reasons of real numbers, there is no immediate next. And to cover this idea of immediate next, we use quantifiers and we add this special condition to remove those, to remove this wall, okay?
So all right.
Yeah.
So the epsilon depends on the little t, is that right?
Pardon, say it again.
The epsilon depends on the little t.
Yes, yes.
Okay.
So there is so there are two nested quantifiers. There is I can actually add parentheses here. So the condition 2 or 3 is saying that for all t greater than or equal 0, this entire thing has to be true. And for each small t, there exists epsilon. So the epsilon depends on the small t, such that for all big T and for all big T within this interval, P of big T holds. You're right. Actually, the proof is quite simple. I mean, the proof of the real induction is quite simple. I'm sketching it here just for 2 reasons, so that you can have it quite easily accessible, and just to showcase that it's really simple. That's the point. I won't discuss it in detail, but in fact, if you just take the intuition I just explained over the picture, you have the proof. There are some other ways to just so this condition 2 is actually quite I won't say important or anything, but you can weaken it a little bit. So this condition 2 can be weakened a little bit, and you can have some sort of condition 2 star, which is here. Simply by, in fact, it's again I'm making the parallel with the induction over the natural numbers because it's easier to keep in mind. So over the natural numbers, we have the standard induction and we have the strong induction. So the strong induction says if the property is true for 0, 1, 2, 3 all the way to k, then you will prove it for k plus 1. The standard induction, the hypothesis is on k, and you prove it for k plus 1, and you're done. Here, it's more or less the same idea. We can weaken a little bit the condition 2. We have a condition 2 star, or we take it as here, or it's in its contrapositive form. But in fact, the idea remains the same. It's simply that this induction over the non-negative reals I'm presenting here, it's more suitable for my purpose afterwards. Okay. Before characterizing positive invariant sets, I need one construction, at least for this first characterization, that I'm gonna use heavily afterwards. So it's important to understand what this operator is doing. So you can think of it as an operator over sets. It's called insets or inf. I'm gonna use inf later on because just it's inf as written down here. So what's this? What is saying? What's this definition is saying is you take a set S in Rn, and you take all the points in Rn. So you see, you don't have. Sorry for this. You're taking all the points in Rn. You don't necessarily need to be in the set S. The condition is that there exists an epsilon such that for all t between 0 and epsilon, the flow remains within S. Okay, let me do it one more time. So you have the potato here, again S, you have a point inside S, or actually outside of S, but you might think that it could be on the boundary of S or on the closure of S. And all you're saying, you're taking all those points and there exists an epsilon positive. For all t between 0 and epsilon, you have the flow is within S. So you have like a small interval here for which the flow remains inside of S. And this idea captures, or this definition actually of for insets, captures the idea of the immediate next future. So you are at some point in the space, not necessarily in the set S, for which the flow in the immediate next future remains within the set S. This is all it says, okay? Once we have this construction or this operator over set S, we can play with it in several and different ways. So one is I can revert the flow. Instead of talking about in F of the set S, I can define or play around with the reverted flow and talk about in minus F of S. This is the third definition here. It's like the first. I'm just here putting a minus because I'm looking to the timeline and backwards, if you like. We can complement the entire in F of S, right? It's a set. We can talk about its complement and we can define it here. And the formal definition simply flips the quantifiers, right? With respect to the original definition, because I'm complementing a set. The other construction I'm going to need is I can talk about the in F of the complement of S. You see, I'm not complementing the entire set. I'm applying the operator to the complement of my set S. And this is the third one. So again, there is a play with the quantifiers in a kind of a subtle way. So it's not exactly in F of S, but there are obviously some links between complementing the entire in F of S or computing the in F of the complement of S. And one of those relations is emphasized here. So it holds true immediately by the definitions that I presented that in F of the complement of S is always included in the complement of in F of S. And the converse doesn't hold in general. Like for any set S, the converse doesn't hold. And I'm going to give a counterexample. After talking about the first characterization, and when I start discussing the computational aspects, I'm gonna go back to this simply to showcase that we don't have in general, we don't have this inclusion doesn't hold in general. Okay, so we don't have equalities for a general set S. Okay, so I'm ready to state the first characterization, or actually to recall the first characterization because it exists almost, but with a different proof. So what the characterization says is S is a positively invariant set under a flow. I'm not saying that S is open, closed, nice, sublevel set of anything. It's just a set S, any set you like. It's positively invariant if and only if, so of course positively invariant under the flow, if and only if two conditions, two inclusions are satisfied. The first is the set S has to be inside in F of S. And the second one, the complement of S has to be inside the in F of the complement of S if you look at the flow backwards. Okay. The first condition here, so let's still call this first inclusion. This is the second inclusion. The first inclusion makes sense intuitively. So you are within S, you're blowing up a little bit the set, but with respect to the flow, and you're requiring that this this balloon that's blowing up a little bit, right, remains within S. This is what you're saying by this condition, right? And it makes sense for a positive invariant set. If you start within the set S, or if you take any ball within this S and you inflate it a little bit, you will remain within S because S is positively invariant. What might be a little bit weird is the second condition with the S complement included in the minus F, etc., etc. But one intuition to keep in mind is, again, this idea of the wall that I presented earlier for real induction. In fact, it might be true that if you're inflating your balloon within the set S, you will remain within the set S, but you don't really know whether there are some walls and whether this actually holds true for any t greater than or equal 0 or not. And this is where this condition comes into play, because it says it really holds true for all t greater than or equal 0. and there are no such weird walls. That's what's saying. Actually, the proof is very simple, really simple, because it suffices to take as a predicate the flow is an S, and you apply real induction. That's all you need to do. Okay.
I just want to mention that there are 5 minutes remaining for the main part of the talk, but we can of course continue discussion of details.
Yeah.
So just wanted to let you know about the timeline.
Shoot, we started at 46, right? Okay. We have some distributive properties. So the operator in F enjoys some distributive properties. So we can talk about the in F of a conjunction of an intersection, the in F of a join. We don't necessarily have equalities here in general for any sets, but we do have some nice distributive properties that are going to be important for the computational aspects. So I won't detail the counter example where actually this one doesn't. So the inclusion in the other direction is not true, and actually it's the same counter example that works for the complement of the set S. I will leave it here, but just keep in mind that it uses the sign, the topological sign function. So those sets are not really nice in the sense that they are not semi-algebraic, they are not semi-analytic. Okay. Suppose we have a procedure, or we have some ways to compute in-F sets, and we actually do, as I can discuss it later on. So when everything is nice, when the set S is semi-algebraic and my right-hand side of the vector field is polynomial, I have means to effectively compute in-F sets. And since I have means to effectively compute in-F sets, all I need to do to check the positive invariance in those nice settings is to construct in F of S, construct in minus F of S complement, and check for the inclusions. And we can check for the inclusions because we can decide the elimination of quantifiers over the reals. So the problem is decidable. Well, it's decidable, right? But in practice, checking for those inclusions never terminates because the procedure is expensive, etc., etc. So what I'm going to present next is a different characterization that leads itself to a much more efficient algorithm. This one is not based on the in-F construct that I showed you earlier. It's actually based on the notion of exit sets used, for instance, by Conley and the Vasevsky principle. And the idea is slightly different and actually defines, it's also an operator on sets, and it defines, it takes all those points. Now it's not an entire Rn as we had earlier for inf. Now we are really restricting ourselves to sets S. And we're asking for those points from which we're going to leave the set. Okay. So using those constructs, we can actually also characterize, we can also play and have different constructs. So we can have the exit minus F, the exit F entirely complemented, the exit F of S complemented, etc., etc. And this gives us a second characterization, which is as follows. So a set S is positively invariant if and only if both exit sets are empty. Okay, so you don't have an exit set, you cannot go outside the set S. But if you place yourself in S complement and you go backwards, you cannot get outside of S complement. Okay, so this is it's different. Like the point of view is different with respect to what I presented earlier. Again, we do have some distributive properties, albeit slightly complicated, but we do have them. But in fact, it turns out that those distributive properties are going to be interesting for the computational aspects. And again, when everything is polynomial and we have semi-algebraic sets, I can compute the exit sets as I can compute in-F sets. And we do have, again, a second decision procedure for those for characterizing positive invariant sets using exit sets. And you might think that since I need to check the emptiness of sets, I might hit the same wall because I need to remove quantifiers. But in fact, what I would like to terminate with probably is what's interesting about this idea of using exit sets. It's somehow a good balance between fine-grained. So in order to check that a set S, a big set, a semi-algebraic set is empty, I can decompose it into basic semi-algebraic sets and check for the emptiness of each component alone. But in general, the number of those basic semi-algebraic sets is exponential. What's nice about exits, what's nice about the exit sets is that it gives a way to decompose a semi-algebraic set S into not necessarily basic semi-algebraic sets, but somehow smaller sets, which I can check, for which the emptiness check is faster. Right? This is really the main idea. It's a recursive procedure that has a good complexity in the sense that its nesting depth is linear. So I'm not putting it here, I guess. No, it's not here. So it's recursive. Its nesting depth is linear, and the number of chunks, if you like, I would like to, for which I need to check the emptiness, is quadratic. It's not exponential. It's quadratic. Which gives me the following theorem. So all I need to do is to check for the emptiness of those two sets, nothing but that. And each one is a recursive procedure, and it starts with a set S, it decomposes it into chunks and checks for the emptiness of its chunk alone. And this is what makes it computationally very appealing. So as I'm putting it here, so the ESE proposes really a natural trade-off between fine-grained, which really goes to basic semi-algebraic sets, or taking the entire thing and trying to check whether it's empty or whether we have a set inclusion in it. So this is quickly the complexity analysis. So the recursion depth, what I wanted to emphasize, recursion depth of this recursion procedure is linear. And the number of calls to quantifier elimination procedures is quadratic. What are K and M? So here I'm considering a disjunctive normal form, but even if I take a CNF conjunctive normal form for my initial set S, it's gonna be the same, okay? Just one example, we can go through it afterwards. What I want to just show before the end, I guess I still have 2 minutes, right? Or not even 2 minutes? Well, 0 minutes. Just, okay. Okay, just again, back to the droplet example. So using the ECE procedure, it took like 0.3 seconds to prove the falsity. And in fact, it's not a positive invariant set. There is a leak somewhere. Whereas using just the LZZ, so the original characterization, it takes more than 4 hours, and we just killed it because it wasn't returning anything. So you see there is a huge gap in terms of efficiency. Of course, on one example, but still. The rest is 2 other different examples. So this one is the vector field is polynomial, but I have linear shapes. So it's the Maltese cross. And this one is everything is nonlinear, but of course still polynomial. And again, the ECE procedure returns in 7 seconds and proves the invariance of the set, whereas the other one takes more than 30 minutes. That's all for the talk. Thank you very much. And we do have many follow-up and ideas that I will be pleased to discuss. One of which is probably going after DAs, chasing DAs. Thank you very much, and sorry for taking 5 more minutes.
Thank you very much. Thank you very much for the talk. I think we have time for maybe like short question, and for more technical discussion, we postpone until after the rooms. Like short question.
Any application to robotics?
Yes. Applications to robotics where one has a candidate and he or she wants to check whether it's really an invariant. For instance, a safety envelope of a robot, and we want to check whether really all the dynamics of the robot will not touch some boundaries or envelope. Those techniques could be used. So this is one way to go in using those checking procedures is really coming up with a candidate and checking it, like formally proving that it's is a positive invariant set. On the other direction, actually, we might sometimes use these characterizations to generate positive invariant sets. because the characterizations will give us some constraints on the polynomial. Like we start with the polynomial with the symbolic coefficients. We get some constraints on the coefficients, and if we manage to solve the system of constraints on those coefficients, it gives us, by construction, positive invariant sets for the system. So all sorts of, wherever qualitative analysis of ordinary differential equations is important, those ideas and those algorithms might be useful.
Okay, thank you very much. Rodney, so how do we proceed then?
So I'll stop the recording first.